This is problem number 2, page 14, free response notebook, equilibrium. We're starting with magnesium fluoride, solid at equilibrium with magnesium ions and fluoride ions. You should recognize that this is solubility. We're dissolving the magnesium fluoride into aqueous ions. We're given the information that we have at equilibrium 1.21 times 10 to the negative third molar magnesium ions. Now, from that information, we know that we should have twice as much fluoride ions, because for every one magnesium ion that we dissociate 2 fluoride ions. Question A asks us to write the equilibrium expression. So KSP is equal to the concentration of the magnesium 2 plus ion times the concentration of the fluoride ion squared, right? Equilibrium K is always products over reactants raised to their coefficients, leaving out solids and liquids. So it's, in this case, it's only the products. Part B, Part B is asking us to calculate the equilibrium concentration of magnesium 2 plus ions in 1 liter saturated solution of magnesium fluoride, to which 0.1 mole of solid potassium fluoride has been added. Remember that the group 1 metals are highly soluble, so when we add 0.1 mole of solid potassium fluoride, we can assume that that means all of the potassium and all of the fluoride becomes part of the ions. So I set up an ice table, and it's a little bit different. We have our original concentrations, our initial concentration rather, of magnesium ion and of fluoride ion. Now notice on fluoride ion I also added in the 0.1 molar. We had 0.1 moles in 1 liter, so 0.1 molar of fluoride ions. Then in the change part, in the change row, since we have more magnesium and since we have more fluoride, we're going to shift back to solid. We're going to have some of that magnesium ion, some of that fluoride ion falling out of solution and precipitating as solid magnesium fluoride. So under magnesium, minus X. Under fluoride, minus 2x, right? Because for every 1 magnesium ion, we need 2 fluoride ions. Then, under equilibrium, the new equilibrium is going to be the old concentration minus x for magnesium, and for fluoride, it's going to be the old concentration, the initial concentration, minus 2x. So we're going to go down and figure out what the KSP value would be for the normal saturated solution. So back to the initial solution where we had 1.21 10 to the negative third magnesium ion and 2.42 10 to the negative third, that's twice magnesium. For the fluoride ion squared, KSP becomes 7.086 10 to the negative ninth. Now KSP is a constant, so the KSP of the new solution, once we've added the 0.1 mole of fluoride ions per liter, will still be the same. We'll have the same KSP. And to do this, we're going to graph this on the calculator. You can set this up and solve it using a quadratic equation, but why do that? You have a calculator. So this is what the calculator work looks like. In the y equals table, we're going to put y1 equal to the KSP. I put 7.08 10 to the negative ninth. In the y2, we're going to plug in the values for the magnesium ion and the fluoride ion. So I have 1.21 to the 10 to the negative third minus x times 0.10242 minus 2x squared, and then graph it If you need to resize the window on the calculator, resize it now. Then second, trace. Number 5 for intersect. You'll hit enter 3 times, once for the first curve, once for the second curve, once for the guess, and then it will at the bottom give you the value for x. In this case I have 0.00120929 for x, and if I take the original concentration of the magnesium, 1.21 10 to the negative third, minus x, I get a value of 7.08 times 10 to the negative 7th molar for the new concentration of the magnesium ion. And that is what they were asking for. Okay, part C. Predict whether a precipitate of magnesium fluoride will form when 100 milliliters of a 310 to the negative third molar magnesium nitrate solution is mixed with 200 milliliters of a 2 to the negative third molar sodium fluoride solution. Calculations to support your prediction must be shown. So in this case, again, here we have group 1 metal with the fluoride, sodium, which means we'll get all of the fluoride out of that sodium fluoride solution. And we have nitrate, highly soluble anion, so we'll get all of the magnesium out of the magnesium nitrate. So what this means is, let's think of our KSP again. Our KSP, we ended up with 7.08 10 to the negative 9th at 18 degrees. That's still the same KSP. And I'm going to convert the amounts of magnesium and fluoride to molar concentrations in the new solution. So we're adding 100 milliliters to 200 milliliters, so our new total volume is 300 milliliters. So I'm taking, for the magnesium, since there's 1 magnesium per magnesium nitrate, I'm taking 3 times 10 to the negative third times 1 liter, or sorry, times 0.1 liter, which will give us moles of magnesium, divided by 0.3 liters, which will give us the molarity of the magnesium, and that comes to be 1 times 10 to the negative third molar magnesium ions. Do essentially the same thing for the fluoride. So we have 2 times 10 to the negative third molar fluoride times 2 liters, that 0.2 liters that we added, divided by 0.3 total liters, gives me 1.33 10 to the negative third molar fluoride ions. We'll plug this back into the KSP, and when I multiply 1 times 10 to the negative third molar times 1.33 times 10 to the negative third molar squared, I get a KSP. I put Q in front of it because it's not really KSP, it's not at equilibrium. We're kind of seeing, where would this be? Is this more than equilibrium? Is this less than equilibrium? So it's sort of a Q. 1.78 10 to the negative 9th, and 1.78 10 to the negative 9th is less than 7.08 10 to the negative 9th, which means that there is not as much dissolved magnesium and fluoride at 18 degrees as this system could hold, so we will not form a precipitate. No precipitate. And part D says at 27 degrees Celsius, the concentration of magnesium in a saturated solution of magnesium fluoride is 1.17 10 to the negative third. Is the dissolving of magnesium fluoride in water an endothermic or exothermic process? Give an explanation, support your conclusion. So this is really a Le Chatelier question. And remember that Le Chatelier says if we stress equilibrium equation on either side, the balance will shift to minimize the stress. So what we're going to do is pretend like heat is either a product or a reactant. And in this case, let's say heat is a reactant, so that if we wrote the equation, we could say magnesium fluoride at equilibrium with magnesium ions and fluoride ions and heat. Now this means heat is on the reactant side. If we increase the heat, we should shift back toward the solid, meaning we should have less material in solution if we increase the heat. If this is exothermic. And in fact, this is what happens. So when we increase the heat from 18 to 27 degrees Celsius, we go from 1.21 10 to the negative third molar to 1.71 10 to the negative third molar, which means less dissolved magnesium, which means this is an exothermic process. Question number 3. Talk to each other. Do it together.